Anyways, a linear system is two linear equations, sometimes more, but at this level you guys are really only going to see two equations, okay? And this particular system is y equals 2x minus 4 and y equals negative 3x plus 1. Now, when you have multiple equations, the solution is whatever ordered pairs will make both statements true, okay? So, example 1 teaches us how to solve the system. How to solve the system. Here in pre-algebra, the one thing you guys are taught to do is to graph them and then identify the dot, the coordinate, where both lines touch. Okay? The place where both lines intersect is going to be the solution of both equations. I've got y equals 2x minus 4 and y equals negative 3x plus 1. I still have plenty of those little graphs that you can use if you wish. You're going to need them today. So y equals 2x minus 4. Is it in slope-intercept form? Yes or no?
Yeah.
Good. So that means this is the what? Y-intercept. 1, 2, 3, 4. I should have made my line longer. Okay? That's the y-intercept. That means this is the what? Slope. Up to right 1. Up to right 1. Okay, it wasn't quite as neat as I should have been when I drew my lines, but in any case, this is the line that best fits the first equation. Okay, that is the line for the first equation. Okay, the second equation, y equals negative 3x plus 1. Is this equation written in slope-intercept form? Then what is the y-intercept? 1. And the slope is 3, or negative 3, which means down 3, right 1. Down 3, right 1. Oh, look. It shares the exact same point as the other line does. Quite clearly. Okay? Therefore, the solution is where the two lines intersect. That's 1, that's negative 2. So it's 1, negative 2. Okay? We graphed both lines. We saw where both lines intersect, and you identify that as your solution. Okay? 1, negative 2. Let's do another one just like that. We're going to solve another system. Hopefully you're writing this with me. If you're not taking notes, then I'm not sure how to help you. Y equals, here's the next system, 4x plus 2. Y equals 1x plus 2. This one's really obvious. You don't see it yet, but you will. All right. We're gonna graph our first one. And I can't seem to draw a straight line. What's the y-intercept for the first equation? 2. And the slope is up 4 over 1. Okay? That is the line for the first equation. Y-intercept is 2. Slope is 4, which means up 4, right 1. There's your line. Second one. What's the y-intercept? 2. Oh, look, there's the solution. And the slope is 1, which means up 1, right 1. There's your line. The solution is 0, 1, where the two lines intersect. I mean 0, 2, good grief. 0, 2. Okay? So this is 2 examples of solving a system. And for examples 13, or for problems 13 through 21, that's what you're going to do. 13 through 21. Okay? This is problems 13 through 21. Ridiculously easy, yes, especially if you're following along. Bravo, Miss Haley. Okay, moving on. Unfortunately, in the world of mathematics and life, not every problem has a solution. Dun, dun, dun. So example 2 is also involved with that particular group. And example 2 shows you what it looks like if your problem has no solution. What kind of lines do you think would never intersect? Any ideas? Go. Parallel. Bravo. Will never intersect. Indeed. Let's look at example 2. Y equals negative 2x plus 1. Y equals negative 2x plus 5. The rules of parallel lines are that same slope, different y-intercept. If you're savvy, you will notice that. If not, that's okay too. So I've got 2 lines that I have to graph. The first one has a y-intercept of 1 and a slope of 2. Oh, I should have made this a little longer. Negative 2. Down 2, right 1. Okay? Y-intercept, slope brought me to my new line, my new point. Here's the first line. Remember, it says solve by graphing, so unfortunately you do have to graph it. I know some of you are already thinking, well, duh. Okay, the next one is 5 for your y-intercept. 1, 2, 3, 4, 5. Same slope, down 2, right 1. If you did what you've been doing all along, you would discover that your lines are parallel. You would then say no solution. Now, in 13 through 21, where you're going to encounter these mixed in with the ones with solutions, it says to you for you to solve by graphing. I know, I read your mind. What if you already see that it's obviously parallel? Sorry. For practice sake, and when you get to Algebra 1 and Algebra 2, you will thank me that you've done this practice work. Yes?
We can make our own graphs for these, right?
Absolutely. You don't have to use these, but I am going to highly recommend that you are extremely neat. Because if you're not neat with how you do your little hashes, you might not have come up with a parallel line. Do you know what I'm saying? So do something to ensure that you're neat. I love these, but again, you don't have to use them. I do have these on full sheets, by the way, and what are they, Brandy? 6 or 8 on a sheet? Shoot, like 6 on a sheet, I think? 6? Yeah. So if you want a bunch of these and you want to use them for 13, 14, 15, 16, 17, 18, 19, 20, 21, you need like 1.5 sheets. It's fine, whatever you like. I can make more copies, no big deal. Yeah, and then you could staple it to that. It's totally fine, okay? Problems that have no solutions. What about another one just like it? How about this one? Now, lucky I'm telling you it has no solution, but you might not have recognized it. Okay, there's the system. The first one is written in slope-intercept form, so I can hurry up and graph it. It's got this is a big graph. Y-intercept, this first one of 1. Ugh. And the slope is -4. 1, 2, 3, 4, 1. Okay. Boom. Is the second item in slope-intercept form?
No.
What must I do to make it slope-intercept? Class, tell me.
Isolate y.
Isolate y. Isolate 1y to be exact. Y equals -4x plus 5. Okay, at this point, you savvy folk are going to say it's the same slope, it's going to have no solution. But here, you might not have seen that. Okay? Here I am. Y-intercept of 5. 1, 2, 3, 4, 5. Slope is -4. Down 4, right 1. They're like right next to each other, like railroad tracks. Okay? No solution. Those lines will never meet, just like railroad tracks. Okay? There's a third scenario that you might encounter. And that scenario is infinite many solutions. Not all numbers, but infinite many solutions. Here it is. Example 3. Infinite solutions. Okay. I have 2x minus y equals -3. And I have 4x plus 2y equals 6. Nothing fancy about these equations. I am going to isolate y by itself. Now you're saying, well, Mrs. Myers, if you subtract 2x, you have a -y. Is that good enough? No. Must be a positive y. Okay, so I'm going to add 3, which gives me 2x plus 3 minus y equals 0, and I'm going to add y. So the 3's canceled out on the right, the y's canceled out on the left. Okay, this is y equals 2x plus 3. Okay. It cannot be a -y. Y-intercept is 3, slope is 2. One, 2, 3, up 2, right 1. Okay, this is my first line. Okay. The next guy. Is it in slope-intercept form? No, but at least the y is positive. That's good. We're going to add 4x to both sides. And to keep it in the right form, 2y equals 4x plus 6. I need to isolate y by itself, not 2y. Divide by 2. Divide by 2. Divide by 2. Y equals 2x plus 3. Same line. Which means that if I fill in one, let's just say 1, 2, 3, 4, 5. If I solve this equation with 1 and I come up with a 5, right? If I plug in a 1 here, 2 times 1 is 3, 2 plus 3 is 5, right? This will solve that solution, right? Is that the only one? No, what if I plug in, is it -1, 1? I think that's close. 2 times -1 is Yes, negative 1, 1 would work. 2 times negative 1 is negative 2, plus 3 indeed is 1. Okay? And I'm sure if we kept going, we would see that there are a bajillion solutions. This line goes up in infinity. So, infinite, because it's the same line. Okay? Yes, sir?
For the parallel things in example 2,
Yep.
if you can see that it's a little bit
Like it's going to meet somewhere.
than the other one, yeah.
Yeah.
If you like went on for like 10 yards.
They're not going to be that hard. They're all going to be on a standard size graph. Okay? Biggest thing I would say your graphs are going to be maybe 4 or 5 up, down. And if it's going to cross, they're going to make it cross somewhere clear. But you're right. I mean, there could be graphs where the slope is like this. So it would take, and that's more advanced numerically because it's just bigger numbers. But absolutely. Good question. Last thing, example 4. So this is example 4 where we deal with the cost of internet. So the cost is equal to what? Well, Plan A says you pay a fixed amount of $200 and to it you add $30 for every month. Okay? Plan A. The cost is you buy the modem and pay $30 a month. Okay? Plan B, and I'm just getting this from what they've written there, okay? Their cost is equivalent to no fee up front, but $40 a month. Okay? So if I translated this into a y equals a, the a one, it would be y equals 30x plus 200. Okay? Y-intercept of 200. B's cost, if I translated this, y equals 40x plus nothing. Okay? I'm only including that so that you could see it. So how would that work if you graph it? Well, they basically have your monthly is your x. Okay, 1 month, 2 months, 3 months. Okay, and your cost is at y. Okay, I don't know how they've got it graphed, but I'll try and do it the same way they did. I think they did it by 200s. $200, $400, $600, $800. And this is each month, right? Month 1, month 2, month 3, month 4, month 5, month 6, 7, 8. I don't know. Just trying to match it. So, if I try to graph this, it's kind of weird, but if I start with this as my y-intercept and my slope is 30, so up 30 over 1. I only kind of estimated my up 30 because obviously in between here and here is 100 or 300. So a third of the way, it's going to give me a little bit of a slope. All right? This is Plan A. Every passing month, you pay a little more. Plan B, y equals 40x plus 0. So start at 0, there's your y-intercept, and up 40 over 1. So if this is 100, here's 40 over 1. Okay? Now my graph might not be as pretty as theirs, but we're going to see 1, 2, 3, 4, 5, 6. Huh. 10, 20, 30, 40. My scale isn't the same as theirs. They did theirs by 20s. Wait a minute. 5, 10, 15, 20. They did theirs by fives. All right, so if I had done the same scale as theirs, it wouldn't be like this. They did 5, 10, 15, 20. That's what threw me off. 20, 25, 30. So at this point, they're going to be about the same cost. And had I used the same scale, 2,800. The thing about this is it is difficult to kind of visualize when you don't know the exact scale. You just have to decide a scale, and if I had decided a little bit better, it would have worked a little better. But I was trying to copy theirs. Anyway.
It would depend on, like, if you pay $30 per month or $30 per 5 months. So,
Yeah, but the way I just graphed it wrong. I just didn't use the right scale. Okay, so the idea here is A is super expensive until after about the 4th month. After the 20th month. After 20 months, you should have just bought the modem. Okay? Okay? So B was cheap until we got to the 5th month. I'm sorry, the 20th month. 5, 10, 15, 20. Okay? It's weird. Okay? That's the idea. Now I know that seems a little weird. You could even check it to see, but I'm really just more hoping that you can realize how to do this kind of thing and how to make a decision. And you can plug in numbers. You can plug in 1 month here and here. Let's do A. A's cost after 1 month is $230, right? 200 plus 30. B's cost after 1 month is $40. You guys see what I'm saying here? So as you go on, you multiply it by 2, it's 200 plus 60 and 80. Multiply it by 3, 290, now we're up to 120. And you could test it that way as well. Just figure out 1 month, 2 months, 3 months, okay, to verify your graph. Okay?